Predicate logic is a powerful extension of propositional logic. While propositional logic treats whole sentences as indivisible units, predicate logic allows us to analyze the internal structure of propositions. It introduces predicates, variables, quantifiers, and relations, enabling us to formally represent statements about objects, their properties, and the relations between them. Because of this increased expressive power, predicate logic plays a central role in philosophy, mathematics, linguistics, computer science, etc. Predicate logic aims to answer questions such as, how can we formally represent general statements like, all humans are mortal, or some students like the teacher? What follows logically from such statements? What does it mean for a sentence to be logically true or logically false when quantifiers are involved? To address these questions, predicate logic provides a formal language, a precise semantics based on domains and interpretations, and rigorous proof systems. In predicate logic, we distinguish between objects and what we say about them. Objects are represented by individual constants, such as a, b, c, and variables, such as x, y, z. What we say about objects is expressed using predicates. A predicate represents a property or a relation. For example, x is human expresses the property of being human, while x loves y expresses a relation between two individuals. Predicate logic introduces quantifiers to express generality and existence. The universal quantifier is read as for all, and the existential or particular quantifier is read as there exists or there is. Using these tools, we can formally express statements such as, for all x, if x is human, then x is mortal, and there is an x such that x is a student and x likes t, the teacher. The syntax of predicate logic specifies which expressions count as well-formed formulas. Its basic components include terms, variables, individual constants, and sometimes function symbols, predicate symbols, each with a fixed arity, logical connectives, the same as in propositional logic, not, and, or, etc. Quantifiers, the universal and the existential quantifiers. Parentheses for disambiguation. Terms are built from variables, constants, and function symbols. Atomic formulas are formed by applying predicates to terms. Complex formulas are then constructed using logical connectives and quantifiers. The syntax is defined recursively, ensuring that every formula has a precise structure and that there are clear rules for building increasingly complex expressions. The semantics of predicate logic explains how formulas are interpreted and assigned truth values. Unlike propositional logic, predicate logic requires more structure. Central to this is the notion of a domain or universe of discourse, which is a non-empty set of objects that the variables range over. An interpretation function assigns meaning to the non-logical symbols of the language. It specifies which object each individual constant refers to, which function each function symbol represents, which property or relation each predicate symbol corresponds to. A model consists of a domain and an interpretation function. Truth is often defined relative to both an interpretation and an assignment of values to variables. Roughly speaking, a universally quantified sentence, for all xa, is true if and only if a is true for every object in the domain, while an existentially quantified sentence, there is an a, is true if and only if a is true for at least one object in the domain. A sentence of predicate logic is logically true if and only if it is true in every model, that is, under every interpretation and every domain. An example is, for all xpx or not px. A sentence is logically false if and only if it is false in every model. An example is, for all xpx and not px. A sentence is logically contingent if and only if it is true in some models and false in others. An example is, there is an x such that px. These notions generalize the corresponding concepts from propositional logic but are more complex due to the involvement of domains and interpretations. A sentence B is a logical consequence of a set of sentences S if and only if there is no interpretation and domain in which all sentences in S are true and B is false. An argument is valid if and only if its conclusion is a logical consequence of its premises. As in propositional logic, validity depends on logical form rather than factual truth. But in predicate logic, the form includes quantifiers and predicates. Several proof methods are commonly used in predicate logic. Natural deduction systems extend propositional rules with quantifier rules, such as universal instantiation and existential generalization. Axiomatic systems provide axiom schemata and inference rules for deriving all valid formulas. Semantic tableaux systematically attempt to construct a countermodel, showing validity by the impossibility of such a model. Resolution is widely used in automated theorem proving and relies on transforming formulas into a standardized form. Unlike propositional logic, predicate logic does not admit a simple decision procedure based on truth tables. We can distinguish between different forms of predicate logic. Property predicate logic allows only one-place predicates expressing properties of individuals. Relational predicate logic allows predicates of any arity, enabling the representation of relations between multiple objects. Relational predicate logic with identity adds the identity symbol to express equality and inequality. Each extension increases expressive power. Identity, for example, allows us to state that two names refer to the same object or that two objects are distinct. Logicians sometimes distinguish between first-order predicate logic and higher-order predicate logic. In first-order logic, variables range only over individual objects in a domain, such as people, numbers, or physical objects. Predicates apply to these individuals, but we cannot quantify over predicates, properties, relations, or functions themselves. In higher-order logic, variables can range not only over individuals but also over predicates, properties, relations, and functions. This allows us to quantify over properties and relations themselves. Property predicate logic and relational predicate logic share important metalogical properties with full first-order logic. They are sound and complete. All provable sentences are logically valid, and all logically valid sentences are provable. However, unlike propositional logic, full first-order predicate logic is undecidable. There is no general algorithm that can determine for every sentence whether it is logically valid. Higher-order logic generally lacks completeness and decidability. Predicate logic greatly expands the expressive resources of formal logic by allowing us to speak about objects, properties, and relations in a structured way. Through its precise syntax, model theoretic semantics, and rigorous proof systems, it provides a powerful framework for analyzing reasoning, arguments, and theories. Despite its limitations, especially undecidability, predicate logic remains the central formal language for much of contemporary logic and philosophy.